Hello viewers, welcome back to my channel. Quickly, I want to treat a very important aspect in chemistry practical. This will really help you concerning your Waec examination and other examination under qualitative analysis. Now, you are going to be given three aspects, three questions in chemistry practical. The first question is on calculation, which is titration. The second part is a qualitative analysis, while the third part is a general question. Now, I'll quickly treat some vital aspects in qualitative analysis first before I move to calculation. And under qualitative analysis, we really need to know the meaning of qualitative analysis, and that is the testing of testing for cations, anions, or positive and negative radicals in a compound or a salt by using different techniques. So when we use different techniques to analyze or to detect the presence of positive ions and negative ions in a compound or salt, then that is qualitative analysis. And in qualitative analysis, we have some reagents or chemicals that are usually used. You will see that anytime you are given instructions or questions. Now, for Waec, the table may be provided, the table for qualitative analysis, where you have the test, the steps on procedure written down, then spaces will be provided for your answers under observation and inference. Now, so let's look at an example of compound, for instance, and how we test for the ions. So if you are given lead trioxonitrate 5, for instance, now, this is a salt and it contains lead 2 ion and trioxonitrate 5 ion. Now, nobody will tell you when you are given a sample, you will not know the content of that sample. You may be asked to add sort of some chemicals to it, and then based on your reaction, you will deduce what the compound or the ions is meant to be. And that is what we call qualitative analysis, checking the quality or the content of a compound or a salt using different reagents. And so we have different ions that are tested for, apart from the organic qualitative analysis. Under inorganic qualitative analysis, that's where I'm specifying or I'm paying more attention to. Now, under inorganic qualitative analysis, we have two types of ions that are tested for, the anions and the cations. The anions are the negative ions, while the cations are the positive ions. So let's look at the positive ion, for instance. The list of positive ions, lead, calcium, aluminium, zinc. Then we have copper 2. We have iron 2, then iron 3. Now, there are some other positive ions. There are positive ions, sodium ion, potassium ion, and ammonium ion. These 3 ions are they are also tested for, but in this case they will show no reaction. Now, how do we test for these positive ions? What are the reagents we use? We use sodium hydroxide and ammonia solution. The two of them must be in form of solution or in aqueous form. So that's what we call side bench reagents. Those are the 2 common reagents used to test for positive ions. Other reagents or chemicals will be, they may be for the confirmation of each of these ions. And when you add either sodium hydroxide or ammonia to any of these compounds or to any substance you are given, the first thing that should come to your mind when you see sodium hydroxide aqueous or ammonia in aqueous form, and you're asked to add it to any compound, you want to identify positive ions, any of these positive ions. For these 3, they show no reaction with sodium hydroxide or ammonia because they are highly reactive. Can we move on? Now, so from what we have here, these 4 ions, they show a white precipitate. Anytime you add either sodium hydroxide or ammonia solution in aqueous form, they show white precipitate. But I'm going to break this down now. So now, qualitative analysis can be in different form. You may be given a single sample. You may also be given a mixture of 2 samples or 2 salts. Now, when you are given a mixture of 2 salts, it will be single. and labeled A, B, C, or D. Now, when you are given this sample, in the question that you are going to be given, you'll be saying something like, B is a mixture of 2 inorganic salts or whatever you are given. Now, just if you are asked, the first thing you will be asked to do is to add water to this sample. So when you are recording, you will see a table. Either you are given the table or you will record by yourself. So we have the test, we have observation, then we have the inference. Now, under test, the first thing you will see is maybe C or D or B, sample B plus water. It can be 10 cm cube of water or any other volume of water, distilled water. When you add this, please do not omit this step. You are expected to write is the, what kind of solution does it form? Is it a clear solution? Then, under inference, is it when you mix the two salts together, were they soluble? Where did you see any, or did you observe anything? Then here you will conclude under inference. Okay, you saw a colorless, or you see something like the two dissolve, C dissolves to in distilled water to form. Now, we don't know what will be formed here, but immediately you dissolve the two like this. Normally, we used to use two soluble salts. Two soluble salts, when they dissolve in water, they will react together. Double decomposition will take place. I'm going to give you 2 examples of salts in this case that form a single compound, that we can mix together to form a single compound, and then we'll get 2 different things by the time you filter. Now, you will see something like filter. If you are asked to filter, then to form, you can now describe the filtrate. The filtrate is what comes out from the sieve, while the residue is what is retained on the filter paper. Now, to form maybe a colorless filtrate and a white residue. Anytime you mix 2 salts together, let me give you an example of the salt that will give us this answer. Lead trioxonitrate 5, for instance, you are adding it to sodium trioxocarbonate 4. When you add these 2 together, double decomposition will take place. They will break into their ions. You know, if you can't write chemical equation, you really need to learn that. Go back to, I've made some videos on chemical equation, you can learn. So this positive will go to this way. So you get something. No, you don't need this in what I'm talking about, but you need the theoretical knowledge. So these 2 react together, positive and negative ions, to form lead carbonate, and this and this minus, they cancel out, NaNO3. Now, one thing about double decomposition is that the 2 salts given will be soluble. By the time you react them together, something will happen, and then you see changes. Then you see that a filtrate and a residue will be formed. What comes out from the filter is a filtrate, and that is sodium trioxocarbonate, sodium trioxonitrate 5. While what comes out as a residue is a lead trioxocarbonate 4. Now, the 2 salts here are soluble because all trioxonitrate salts are soluble. So lead trioxonitrate is soluble in water. Then all salts of sodium are also soluble, just like all sorts of potassium and ammonium ion are soluble. And that's why the 2 soluble salts react together to form a soluble and an insoluble salt. And that the insoluble salt here is the residue which comes out, is retained on the filter paper, because reactions will take place. They will exchange radicals, and then this one will come out as the filtrate. From there, you should have the knowledge that, okay, this is what is inside it. The filtrate definitely contains some ions. Assuming you don't even have a foreknowledge of this compound, you don't know what is inside sample C. I'm giving you an example that if this is made up of sample C, if these 2 salts made up of sample C, that is, I'm just explaining what you will be expecting. But in case you don't even have an idea of what sample C is made up of, you know that once you add water you will write whether it dissolves or does not dissolve. When you filter, you will describe the filtrate and the residue. You can now write, okay, C is a mixture of two soluble salts. Now, from what you have here, you have just acted normally without knowing what B is made up of. Permit me to change this back to B. You don't know what it is made up of. You only followed instruction. Now, I'm going to teach you what you will now be expecting. You know that when you filter, something came out as filtrate and something else came out as residue. So how will you know what is inside the filtrate and what is inside the residue? Now, I told you something at the beginning, that anytime you see sodium hydroxide or ammonia, you are testing for positive ion. Assuming our filtrate is sodium triazonitrate 5. Definitely we test for the sodium ion and the triazonitrate 5 ions. And so if you are asked to add, maybe take a portion of the filtrate, add sodium hydroxide in drops, then in excess. Definitely, when you don't see any reaction, you will know that even when you have sodium hydroxide, that is sodium. You are testing for sodium in the filtrate. Because whenever you see these two, you are testing for positive ion. And this is a positive ion in the filtrate. What if this is a negative ion in the filtrate? So when you are asked to use either sodium hydroxide or ammonia, there will be no visible reaction because that is normal. Sodium does not give any reaction. But at times, you may not be asked to use sodium hydroxide or ammonia at all because they already know that sodium is silent, does not give any reaction. So we may just focus on this. So I'll tell you the reagent that I used to test for triazonitrate 5. But before I move to the negative part, because it's a negative part, I want to quickly settle this. So there's something I want to call your attention to. When you are recording, you will see if you are adding maybe filtrate plus sodium hydroxide, write AQ at the front in case the test is not written for you. Now, you must separate your work in drops first. In excess, when you add something in excess, you are trying to test whether it is soluble or not. When you add it in drop, you will see a color change. But when you add it in excess, whatever you are adding in excess, maybe silent reagent like sodium hydroxide and ammonia, you are adding it so as to check whether it is soluble or not. So you have different answers here and different answers. So you are expecting 4 answers here in drops, in excess, in drops, and in the inference for the 2. Now, so what are the color changes you will see? Let me tell you this. If you are working with a compound that contains lead, take for instance, our residue is lead triazocarbonate. This is the residue, and this is the filtrate. So it means we are testing for lead, and we are testing for triazocarbonate 4. So lead usually give a white powdery precipitate when you add sodium hydroxide in drop or in excess. And when you add it in excess, it will be soluble in excess sodium hydroxide. Now, calcium. So, lead usually give white powdery precipitate. Calcium also gives a white powdery precipitate, which is insoluble in excess sodium hydroxide. Lead gives white powder. When you see a white powdery precipitate, something like paracetamol dissolved in water or chalk dissolved in water, and then the particles are settled at the base of the container, and then you have a cloudy liquid at the top of the container, that is probably calcium or lead. So when you add sodium hydroxide in drop, what you're expected to write is this. That is if you are working with the residue, for instance. This is a sample of the residue. What is inside the filter paper? After you filter, you fold your filter paper and then you filter. You know, filtrate is out and is like a clear liquid because this compound is soluble. It's like a clear liquid, just like water. And then we have sodium and triazonitrate 5 ion inside it, where sodium is silent. It does not react with sodium hydroxide or ammonia. And I told you that we use sodium hydroxide and ammonia to test for a positive ion. So when you see in the question that you are asked to use sodium hydroxide or ammonia, you are testing for positive ion. And in your filtrate, the one that comes out of the filter paper, it contains sodium ion and trioxonitrify ion, and the sodium is silent. You will see that when you add sodium hydroxide in drop or in excess, or ammonia in drop and in excess, there will be no reaction at all. You know color change. That is sodium, potassium, or ammonium ion present. Now, when you are asked to use other chemicals, you are working on the trioxonitric fact. But I want to settle the positive aspect first. So for your residue, if you are asked to add sodium hydroxide to the residue, that is what is inside the filter paper, you were asked to add sodium hydroxide in drops and in excess. If it contains lead, you see a white powdery precipitate that is soluble. When you add it, sodium hydroxide in excess, it will clear off. It will become soluble. Everything will dissolve. But if it is calcium, even when you add sodium hydroxide in drop or in excess, it will not dissolve. It is insoluble. Now, so I told you that two ions form white powdery precipitates, lead and calcium. But lead, when you add sodium hydroxide in excess, it will dissolve and clear off. So when you are having your answer, assuming you have residue here now of sodium plus sodium hydroxide in drops and in excess. In drops, you will write whatever you see, maybe a white powdery precipitate. Then in excess, soluble in excess sodium hydroxide. You can see the answers are on two different lines and you get your 2 marks. Now for your answers too, you have your answer. So let me quickly run through this before I go back to the table. Now, aluminium and zinc, they also form white precipitate with sodium hydroxide and ammonia. But aluminium and zinc, they form white gelatinous precipitate, just something like a gel. And then when you add sodium hydroxide in drop, they form white gelatinous precipitate. But when you add it in excess, the white gelatinous precipitate will become soluble. They will clear off. Now, when you add ammonia to these 4 ions, lead in ammonia in drops, it will become a white powdery precipitate. That is what will be formed. When you now add it in excess, if it is lead, it will be a white powdery precipitate insoluble in excess. When you add ammonia to calcium, there will be no visible reaction due to turbidity. It will not react. Now, when you add ammonia to any compound containing aluminium, it will form a white gelatinous precipitate, and the precipitate will be what? Insoluble, if it is ammonia. Then if it is zinc, the gelatinous precipitate will be soluble. So with sodium hydroxide, they all form white precipitate. These two forms white powder precipitate, lead and calcium, while the remaining two, aluminum and zinc, or zinc and aluminum, form white gelatinous precipitate. And in excess of sodium hydroxide, they all become soluble except calcium. Now with ammonia, the two of them forms, this calcium will not react at all with ammonia, while lead will form white powder precipitate and it will be insoluble. Now, aluminium also form white powder precipitate and is insoluble. Only zinc will form a white powder precipitate. Sorry, white gelatinous precipitate for aluminium and zinc, but that of zinc will be soluble in ammonia. Now, copper will form a blue color. Iron 2 will form a green color, dirty green precipitate. Copper is blue precipitate, while iron 3 is reddish brown precipitate. Now, they all have different reactions. Copper dissolves in sodium hydroxide. When you add it in drop, it will form a blue precipitate, a pale blue precipitate. When you add it in excess, sodium hydroxide in excess, it will form a pale blue precipitate which is insoluble in excess. When you add sodium hydroxide to iron and iron 2 and 3 in drops, they will form reddish brown precipitate and then green precipitate respectively. When you add them in excess, they will remain insoluble. But when you add ammonia to copper, copper will dissolve. The blue precipitate will dissolve to, that's when you add ammonia in excess. The blue precipitate will dissolve to form a deep blue solution, while others still behave the same way. They form their colors, respective colors. The color of green is reddish, the color of iron is green, while that of ion 3 is reddish brown. That of ion 2 is green, dirty green. Now, so this remains insoluble because I told you there are 2 ions that are used to test for positive ions. They are sodium hydroxide and ammonia. So each time you seek sodium hydroxide and ammonia in your question, just know you are testing for positive ions. And when you are given a single sample and you have to add water and filter, you are expecting 2 things. You are expecting residue and filtrate. That is, not everything will dissolve. It will dissolve at first because you have a combination of, the example I gave you now is a combination of 2 soluble salts. And double decomposition will take place, and a reaction will take place, and something else will be formed, which will come out as part of the residue. It will be on the filter paper. It will not pass through the paper. That's the residue. It will be left to dry while you are working on the filtrate, the one that comes out with the distilled water. That is also a salt, and then that one is soluble. So you will work on filtrate first before you move to residue. And if you are given 2 sample, you are given a sample, which is sample B, for instance, and it contains 2 soluble salts, I'm giving you the reaction that I reacted the 2 together, that then the composition will take place, and then you get an insoluble residue and a soluble filtrate. And so for your filtrate, you know the reaction. Once you see the color changes, which I've described, you will know. And how will you know what you are testing for, whether positive or negative? When you see these 2 compounds, sodium hydroxide and ammonia, you are testing for the positive side. And then it's now left for you to see from the color changes. I've described the 4 ions that gives white precipitate. So to test for the negative radicals, now under your filtrate, the one that comes out of the filter paper, we will be testing for this trioxonitrate 5. And to test for trioxonitrate 5, we use barium chloride followed by dilute HCl or HNO3. And they usually give a white precipitate. Another thing you can be asked to do, you will write white precipitate under inference, and then under observation, and then under inference, NO3 minus or other ions present. Now, but you may be asked to eat this compound, to boil it. You know, it will be in form of liquid. You may be asked to boil it. Anytime you are boiling or you are adding acid, watch out for the liberation of a gas. And the only gas that will be liberated from trioxonitrate 5 of sodium is oxygen. And you will get something like this, NaNO2 and oxygen. So it's only oxygen gas that can be liberated from a trioxonitrate 5 of sodium. If it's trioxonitrate 5 of other ions that are moderately reactive, other metals are moderately reactive, it can liberate NO2 gas, that's nitrogen 4 oxide gas, that is a brown gas. But for sodium trioxonitrate 5, which is your filtrate, it is only oxygen gas that can be liberated, and it's oxygen gas. Now, if you are testing for, if you are asked to eat or add dilute hydrochloric acid, observe the vapor coming out. Bring a blue and red litmus paper that is moistened, that is you have wet with distilled water. Bring it close to the tip. If there's a color change, it means the gas is either acidic or alkaline. If there's no color change, and so that's why when you are recording gases, maybe you write a colorless, and you will have to write a colorless and an odorless gas, which make a pop sound, which rekindles a glowing splint, and it is neutral to litmus paper. Those are the 4 aspects of the test. Any test you are testing for, that is how you describe them. So for oxygen is a colorless and a odorless gas, which is neutral to litmus paper and rekindles a glowing splint. Now, you can bring a splint, just like plywood, a burning splint. You put it in the flame, you put out the flame, then when it's glowing, bring it close to the mouth of the vapor that is coming out when you are eating the filtrate. If the flame comes up alive, or it means it is rekindled. So that is oxygen. So under inference, you write oxygen gas from NO3 minus. It is also very important for you to know the charges on these ions. Now, if it is residue you are working on, definitely you are testing for the positive ions of the residue, that's the lead, and also the CO3 2 minus on the residue. And when you are testing for CO3 2 minus, anytime you see silver, you see Anytime you see silver nitrate, you are testing for chloride ion, but we are not working with chloride ion in this example. So in this case now, we will use barium chloride. If you are testing for the residue, you will see something like add barium chloride followed by dilute HNO3. When you see that, now on the first line, barium chloride, plus dilute hydrogen triiodine-95, you will see a white precipitate. Now there are different ions that form white precipitate with barium chloride and dilute HNO3. And when you add dilute HNO3, you will see whether it is soluble or not. Now, if it remains insoluble, it is SO4 2-. But if it is soluble, when you add barium chloride and then you add dilute HNO3 and becomes soluble, that is, you are going to record 4 ions. So let me pretend as if I'm working on the residue now. So to a portion of the residue, from C plus barium chloride, you can see AQ at the front, plus dilute either ACl or HNO3. You will see a white precipitate, soluble in dilute HNO3. Now, it means that, don't forget I told you that this is a residue, and this is this part I'm working on. Anytime you see barium chloride and dilute HNO3, we are working on CO3 2- of the residue. And so, this is what you write. Now, if you have things like this, if you have a white precipitate, you can write CO3 2-. These are the various ions that form white precipitate. SO4 2-, HCO3-, or SO3 2- are present. You write at least 4 or 3. Now, if it is soluble, these ions are still present except SO4. Now, if it is insoluble in HNO3, then it's SO4 2- that is present. If it's soluble, then you still repeat other 3 ions and you get your marks here. You can see 2 different lines of answer. Now, it is now here that, they are still in group. We will now run a confirmatory test. You might now be asked to add any other compound or eat. Add dilute HNO3 and eat. I told you whenever you're adding acid and eating, watch out for the evolution of a gas. So if you are asked to eat, in this case, you have to describe the gas under the influence. If you see vapor coming out when you are boiling it using a boiling tube, and you are using a test tube holder and you are eating it, you will see that a vapor will be coming out. If the vapor is coming out, bring a blue and red litmus paper close to it. Perceive the odor and the color. Then bring a blue and red litmus paper close to it. And the blue and red litmus paper must be moistened, that is wet with litmus paper. If you bring it close to it and you see that there is a change of blue litmus paper from blue to red, that is slightly acidic, and that's like that. It means CO2 is present, because the sample we are working with under our residue contains CO3 2-. It means CO2 is present, provided that, I said is a colorless and a odorless gas which turns blue litmus paper red. Then the last one, if it turns lime water milky, that's calcium hydroxide in solution. When you bring it close to it, maybe inside a capillary tube, it will turn the lime water milky. That is the calcium hydroxide, which is the lime water. If it is a clear solution, when brought near CO2, it will change it to a milky coloration due to the formation of calcium hydrogen triiodocarbonate 4. So those are the 4 things you write under observation. If you are eating and adding acid, or you are eating directly alone or adding acid only, watch out for the evolution. So in that case, you get 4 marks. Colorless and odorless gas, which turns blue litmus paper red and lime water milky, that's 4 marks. Then under your inference will be CO2 gas from CO3 2-. And the last aspect is this. We can carry out a confirmatory test on CO3 2-. That's the use of phenolphthalein indicator. Anytime a phenolphthalein indicator is used in that case, I think you're going to get a pink appearance when you are testing for it. So all you need to know is to calm down and identify the ions. Once you see barium chloride followed by dilute HCl, you are working with CO3 2-, SO3 2-, and so on. When you see barium. When you see you are asked to eat or carry out a brown ring experiment, but in this case we can't carry out a brown ring experiment using concentrated H2SO4 and freshly prepared iron 2 tetraoxide 6. We can't carry it out for trioxonitrate. The only thing we can be asked to do under the filtrate is to eat and test for oxygen. So when you see that, you know you are testing for oxygen under your, don't forget what a filtrate is. It's coming out from the filter paper as a clear liquid, while the residue is on the filter paper, the one that it did not dissolve. So the residue contains lead and trioxocarbonate 4, while the filtrate contains sodium and trioxonitrate 5 ion. And when you are working on positive ions, we use sodium hydroxide and ammonia to test for them. When you are working on negative ion, if it is CO3 2-, you use barium chloride and dilute HNO3 or dilute HCl. If it is chloride ion, you use silver nitrate, trioxonitrate 5, and dilute HCl or dilute HNO3. If it is SO3 2-, and so on, we use barium chloride plus dilute HCl, and so on and so forth. Then, apart from carrying out confirmatory tests on them, and anytime you are eating, watch out for the liberation of a gas. Anytime you add dilute HCl, watch out for the liberation of a gas, and write your under your observation. Never mention clear solution, but you can write a colorless solution is formed, and then your inference will be the ions that are formed with the correct charges on them. And if you cannot spell precipitate, please do well to learn the spellings of precipitate, write it. And don't forget, if you are recording the test by yourself, test, observation, inference. At the front of sodium hydroxide and dilute any other reagents used, put your aqueous, whether in ammonia or sodium hydroxide. I wish you all the best in your exam. For your titration, that's quantitative analysis, which is titration. If you are working on redox reaction, never mention acid or base. And your table, you know the rules following the table. Your table must be well recorded. Don't use two values that are in concordance, that is, they have a difference of 0.1, 0.20 as a difference. That's plus or minus. And for your calculation as well, you have three formulas that can be useful for you. That's the CAVA, provided whatever is inside the burette is labeled A, and whatever is inside the pipette is labeled B. Now, this will be the number of moles from the balanced equation of reaction. If you are given an equation of reaction for any titration, and if you are not given any equation of reaction, you are expected to write and balance it. From a balanced equation of reaction, you write the number of mole of acid. That is, if there's nothing beside the acid, then it means it is 1. And sorry, number of mole of the A and number of mole of B. Now, we are not working with acid and base if you are working with redox titration, for instance. And so it's just a matter of titrating reducing agent with oxidizing agent. And the oxidizing agent, for instance, in KMNO4, for instance, now, will be inside the burette, which has a purple color, and the iron 2 tetraoxide 6 will be pipetted and the green solution. Now, and the iron 2 can be acidified. You can add, after pipetting the iron 2, you can add a certain volume of dilute H2SO4 or tetraoxide 6 acid to it before you now titrate with the KMNO4, which is inside the burette. And always take note of your burette. Make sure that it's properly filled and correct readings are taken. And then when you start titrating, you never look at the burette, but look at the color changes. Be shaking, add few drop, you shake until you get a color change. When you add a drop and then you see pink appearing and the pink disappears, that is not the end point. But by the time you add a drop again and you shake and then the pink, even if it is pale pink, showed up, that is your titer point. You don't need to overshoot by adding more KMNO4 to get a pink color, a deep pink color. That is not how to titrate. You are overshooting in that case. At the point where pink color appear and it's permanent, that is, it's even if it's pale but it's permanent, it's not disappearing again, that is the end point, because that is the color you're going to get at the end. And for your formulas, just like I mentioned, take note of two things. Correct substitution, that is the correct value. This will be the average volume of acid that you get from your table. When you have a table, burette readings, you have rough titration, You have first titration, please always write it in full. Second titration, third titration. Now, this is the final volume of A used. This is the initial volume of A used. And this is the volume of A used. Now, I will advise you to always fill your burette up to 0 points, then titrate wherever it stopped. For instance, if it stopped at 15.10, there's nothing like 15.12, 15.13, just 15.1, 0.2, 0.3, 0.4 until you get to 16. So 10, by the time you are deducting this, don't forget something is missing here, which is what? cm cube. Very, very important that you put unit in everything. cm cube must not be omitted. So from here, your final answer here is 15.10. Let's assume you fill your burette up to 0 point again, and then you titrate again, you get 15.7, 14.70. This is 14.70. Then you fill it up again, you titrate, and you get 14.50. So 14.50 by the time you deduct, then fill it up again, or depends. You can start from 10. You have to deduct your answer. Whatever you get will be the determinant. And then you get 15.60. So you can see now that these two values are in concordance. Even the second and third, sorry, the first and third are also in concordance because there's a difference of just 0.1 or 0.2. So you can use the last two to find your average. That is average volume of A used will be sum of the last two that are in concordance. Never use your rough titration as part of the concordant value. Add them together and divide by 2. You get your final, which must be in cm cube. If the volume is not, the unit is not there, cm cube. That is, when you are calculating the average, add them together, add these last two values together and divide by 2. If you are adding the three values, make sure they are in concordance. A difference of 0.2 plus or minus, or 0.1 plus or minus. Add the 3 and divide by 3, and your answer must be in cm cube. That is the unit. If there is no unit yet, there will be no mark. So I said this is the first formula that will be very useful, but I'm not saying you must use this formula for the first question. It depends on the question given to you. If in the question you have to calculate molar concentration, this volume of A is the volume that you get here when you calculate your average volume. That's what we call titer value. That is VA. Why CB is the molar concentration of B. If question will be given, the values will be given in the question, it may be mole per dm cube, mole/dm cube. Why VB is the volume of the pipettes. Pipettes. Some schools use 25, some schools use 20. And this is the number of mole of acid and base in the equation of reaction, or number of mole of A and B, the oxidizing agent and the reducing agent, in the equation of reaction. So correct substitution usually give 1 mark. Then another one is subject of formula. Maybe you want to calculate CA. Okay, make CA subject of formula and put other value. CA equals, maybe CA is here, multiplied by volume of acid. Maybe your titer value is 14.50. And then I'm just imagining, I'm just assuming anyway, the concentration of it maybe 0.010, and then volume of base is 25. That's volume of your pipette, and then number of mole is 1/5, for instance. But this is correct substitution 1 mark. By the time you cross multiply, you end up getting CA equals to 0.010 times 25 times 1 over 14.5 times 5. This is subject of formula, which is another 1 mark. Then the next one is getting the final answer correct to 2 decimal places. If your answer is 0, I'm just imagining, I'm not using calculator, 0.101. So, or 0.1. If that is your final answer, your answer will be 0.100, and it must be mole per dm cube if you are calculating molar concentration. Then for other formulas that are going to be very useful, though I may not be able to say when you will use them, they are molar concentration, which is a mole per dm cube, equals to mass concentration. That one is usually in gram per dm cube over molar mass. Now, one thing about the molar mass is always in gram per mole. If you know the elements you are working with, you can work out the molar mass of it. The information will be given under the question. Maybe K will be 39, Mn, that's manganese, will be 55, oxygen is 16, multiplied by 4. You get your molar mass, and molar mass should be calculated first. If you are going to use this formula, calculate it and put the correct unit, which is gram per mole. If there's no unit there, no mark. And that is 1 mark before you use it in this calculation. So if you want to calculate molar mass concentration, you can always get maybe your molar concentration is here, and then you work out molar mass, multiply, and then you get your answer. So this is one formula. And the last formula which is going to be useful is N is equal to CV over 1000, where N is number of mole, and this is molar concentration multiplied by volume over 1000. So this is also going to be very useful for you, depending on the question that is given to you. And in case you are not given gram per dm cube means 1000 cm cube. If mass concentration is not given in gram, maybe A is a solution of 3.15 gram in 500 cm cube. You can see you can't use 3.15 in your calculation directly. You need to convert it to 1000 by multiplying 3.15 by 2, because how many 500 can you get in 1000? That's 2. It must be in per 1000 cm cube or per dm cube. That's gram per dm cube before you can use it in your calculation. I wish you all the best in your exam. Calm down when it comes to calculation and work out the correct formula to use for the first question, because your answers will affect other subsequent questions. And abide by the rules and regulations. Let's not forget this. Never alter your values. Don't change value. Don't change. So I will advise you to use pencil first, but make sure you change the pencil back to pen. If you submit with pencil, that is -4, when the table is already 8 marks. Now, if you are calculating and there's a change in value, please never use tip X or try to change the value, and never you cancel your table. So that is why when you are recording, record with pencil first, and then use your biro to write on the pencil when you are sure of your answer. When doing that, after writing, use your eraser to clean it. Don't leave the pencil, don't submit with pencil, don't answer your questions with pencil. I wish you all the best in your exam. Don't forget to subscribe to my channel and watch out for interesting topics in preparation for your forthcoming Waec theory and objective questions. Share my videos to people who are in need of it. Like my video and also subscribe if you are yet to subscribe to the channel. Thank you.